Okay, so as in the last video, we have derived the unit for the capacitance of a capacitor, and we got to know that the unit of capacitance of a capacitor is equal to farad, and that is equivalent to coulomb per unit volt, right? In today's video, we're gonna see how the capacitance of capacitor depends on the distance between the plates, area of the plates, right? Is that directly proportional to these two quantities or inversely proportional to these two quantities? Today we're going to discuss everything in this video. Alright, so before going towards that, we need to understand the diagram again so that we can have our charge density, because with that formula we will be driving our entire equation, what capacitance of a capacitor depends on. Alright, so here I am making. Okay, so we have initially considered two opposite charged parallel plates. So this is one plate, this is another plate, right? These are two oppositely charged parallel plates. One has a positive charge and a second one has a negative charge, because they both are oppositely charged parallel plates. The positive plate of the capacitor is connected to the positive terminal of the battery, right? And the negative plate of the capacitor is connected with the negative terminal of the battery and stores a negative charge. These both two oppositely charged parallel plates are separated by a very small distance called d. Alright, so this is what we have the diagram of the capacitance, right? The charge will gonna move from the higher potential to the lower potential, right? This is our diagram. Now we know that the medium between these two plates would either be air or a vacuum. Alright, will either be air or vacuum, right? And this is the distance we have. Think that this is plate A and this is plate B. We know that what is the formula of the charge density? It is sigma is equal to charge per unit area. Basically anything divided by area we get its density, right? If I do talk about current density, that would be current per unit area, that would be current density. Magnetic flux density would be magnetic flux per unit area, that would be magnetic flux density. Alright, anything divided by area would give us density, right? Now we're going to drive our equation. We have initially learned that the charge stored on the plate of the capacitor would be directly proportional to the potential difference provided to it. Alright, so that we are going to write here, the charges which will be stored on the plate of the capacitor would be directly proportional to the potential difference provided to it. Alright, when we remove this proportionality sign, we have got our constant and is equal to sign. So charge is equal to CV. We want capacitance of a capacitor, so C is equal to Q over V, right? This is, we have got the capacitance of a capacitor, which is the ratio between the charge stored on the plate of the capacitor and the potential difference provided to it. Alright, now we need to substitute the equation of density here. We know that charge density is equal to charge per unit area, but here we have charge, so we need to drive this equation for the charge. So area is dividing here by the charge, when we will go there it will be multiplied. So charge is equal to sigma into area, right? Now this equation we will be substituting in our first equation. Let's suppose this is our equation number 1, right? This is equation number 1. Now we will be substituting the value of charge in equation 1, right? So let's substitute the value of it. We know that C is equal to Q per unit V. So Q is equal to sigma A per unit V, right? So now we have got our second equation as well, which is C is equal to sigma multiply by area per unit potential difference V volt, right? This is our equation number 2. This is our equation number 2. Let me highlight this as well. We have got equation number 2, right? Now we know that potential difference is what? Potential difference is basically the dot product of electric field intensity and the displacement, right? Potential difference is nothing but it is the dot product of electric field intensity and the displacement, right? So let's highlight this. Now let's substitute this V value in the equation number 2, right? So we are going to substitute the value of potential difference. Now substituting the value of V, in equation 2, right? In equation 2. So now let's substitute the value of it. So C is equal to sigma into A per unit. Instead of V, we need to write E dot displacement, right? Now we have got it, right? Either you can write this or not. It does not matter, right? So now we also know that what this parallel plate electric field is equal to. We know that this electric field is equal to sigma per unit epsilon naught, right? This is what? This is parallel plate. Right? And this is what we call the Gauss application, right? Gauss law application. Gauss law application. This is very important, right? So let me highlight this. Now let's substitute this value instead of E in equation number 3, right? This was equation number 3 we got. Let's highlight this third equation with yellow highlighter, right? Now substituting E's value in equation 3, right? In equation 3. So let's substitute the value of it. So we got that C is equal to sigma into A per unit. Instead of this E, we need to write sigma upon epsilon naught into D, right? Sigma cancel with sigma. This epsilon naught will go up and it would be multiplied. So here we got that C is equal to epsilon naught into A per unit D, right? This is what we have got till now. Now because of this equation, we are getting that what capacitance depends upon directly and inversely. Because of this equation, we got that capacitance of a capacitor is directly proportional to the area of the plates, right? Very important. Because of for this only we have derived this entire equation, and capacitance of a capacitor is inversely proportional to the distance between the plates. We initially learned that capacitance of a capacitor depends on 3 things: the area of the plates, the distance between the plates, and the material of the medium between the plates, right? Now we have got that capacitance of a capacitor is directly proportional to the area of the plates. Wait, let me highlight this two together. So capacitance of a capacitor is directly proportional to the area of the plates, and capacitance of a capacitor is inversely proportional to the distance between the plates, right? So the area, if the area of the plates would be more, the capacitance would be more as well, and if the distance between the between the two plates of the capacitor would be higher, the capacitance value would be lower, right? Because it is inversely proportional, right? And what is the thing on what capacitance does not depend? Capacitance does not depend on the thickness of the plate. So this was all for today. This equation, this entire equation we just derived since we weren't known that what capacitance of a capacitor depends upon directly and inversely, right? So by deriving this entire equation we got to know that capacitance of a capacitor is directly proportional to the area and inversely proportional to the distance. Means if you increase the area, the capacitance of a capacitor would be increased, and if you increase the distance, the capacitance of a capacitor would be decreased. But if you're going to decrease the distance, the capacitance of a capacitor would be increased. So this was all for today. In the next video we will gonna learn if we're gonna place a dielectric plate between these two oppositely charged plates, what will gonna happen. In next video we're gonna drive that.